Hello and welcome back. A few videos ago, I was trying to make an external reference on this UNI-T signal generator. This is the 60 MHz version, so it's the UTG962E. We already discovered that the internal clock runs on 50 MHz, which is not necessarily very convenient if you run all your other lab references on 10 MHz. But there is a solution for that. I will show you later. I wasn't necessarily successful. And yeah, people commented also, and it's probably maybe even something silly, like yeah, I made the assumption that the metal parts were all grounded, and maybe that is not the case. So I maybe the only thing I did wrong is probably that I did not have a good ground point. So well, today I'm gonna try to do this, and then also find maybe a cheaper solution than I did before with my 6-channel PLL. So well, I added something to my workbench, and that is here. This is a 8-channel USB charger, and I already like it. And also I made a power plug right here because sometimes you're just working here on your bench and then you need power. I have for the normal Euro plugs, I have here some extras, and if I need 12 volts, I have here 12 volt DC plug that is just connected to my 12 volt in the lab everywhere. So I have one power for that. The only thing that was missing was one power point for 5 volts, and that's now here. And the cool thing is, it even displays the current it's using. So also for the little function generator right here, it even has one high power port. So if I take this out, so we do not get disturbed, and then we have a nice display how much current it's using. So that's also very convenient, and I can also connect all my others. It can do a lot of power. I forgot to see. I have here how much. It can do 40 watts, so that is pretty much. Okay, now first I'm just gonna open it up. Well, I know from last time that after you have taken out all the screws, you need to push in the middle here, and in the bottom in the middle, and then you can just open it. Because the other time I almost broke my flat cable because I pulled so hard and then it went open. So let's see if I can do that more smooth this time. Most of the work has been done, so the probing has been done. We found the correct point. The switch is already in. The exit is already there. So, or the entrance actually. It's an input. And the switch I did that I can also use internal, of course, because maybe if you take it somewhere on the road and you don't have your external reference, you can still use it. So that's why I usually have a switch to switch it over. And now I need to push in the bottom and the top, and then here it is. There it goes. And again, I almost break the flat cable. Really. Okay. Okay, here we go. Okay. I hope I didn't break it because, well, it's flexible. I will zoom in. So the ground point I took is maybe not a ground point, and then of course if you insert a wave, it is just not reference to the correct ground. I just took here the USB, yeah, as a ground point, but maybe that is not. So I will take out the circuit board. I need to take out the switch first, and then I can take it out. Well, meanwhile, the soldering iron is heating. Just going to do some measurements. I have the ground here on the BNC and the ground on the USB. And it's indeed not the same ground. It's not even connected at all. And if I take the other ground of the, let's see if I can find it. Ground of the oscillator. Now I need to make more space. I cannot reach it. No, it's not connected to the ground. Okay, so we might have found something. Very good, very good, very good. Okay, I can get it from there. Let me get the part of this cable first. Put it here. I think it was. Meanwhile, this is. Take the switch out, and then we can take the whole board out. You need to flip the switch just to create that extra millimeter of space, and then you can just, oops, there it is. Okay, let me get the microscope. Okay, switch this on. So here we connected the wires close to the oscillator, and this is the oscillator ground. And it does look like it is all connected, but it is not, because if you look here, that is exactly the problem. It is not connected to ground. If you look around, there is a space there. We should be able to see exactly the same in the bottom as well. Yeah. Okay, that is exactly the problem. Yeah. So the shielding I used is not connected, and I've read somewhere they do this because if you connect it to your computer, and you can somehow get a loop if you're also doing measuring with your USB devices, and well, they just don't want to have loops, ground loops. Well, there is a row of pins here, and with a bit of luck, and you can probably assume again that one of these pins is a ground pin, and if we are really lucky, it is the first one, and otherwise maybe we can pick it from the DC plug. So maybe if we have a better look here. So we have a better look. Here is the row of pins. So the last one could be, or the first one right there. So let's look from the bottom. Then it becomes the top one. Here is the USB. Where is my row of pins? Here. Yes. First pin is indeed ground. It is connected also to the DC right there. That is DC ground. Well, now I'm gonna measure between the ground of the oscillator and the ground of that pin, and if that is indeed the same, then we're gonna use that pin. Well, now just measuring, well, that's really simple, of course, and I like that I put a little bit of a longer wire between the oscillator, because then I'm more flexible right now. So if I go to the ground of the, let me get the pin and the ground of the oscillator. Yes, that is the same ground. And is the ground of the oscillator also BNC ground? Yes, it is. Okay, that's great, because in the end, because all my devices have external reference, So all the B and C grounds will be connected to the ground of the reference as well. So if this somehow there was a reason that it was isolated, then the external reference would just damage that by connecting that, but that is no problem. Ground is ground. B and C ground is also oscillator ground. So perfect. I don't foresee any problems there. Okay, I will try to give you a little bit a better look. So we put this back in. So, choop choop, that's it. I'm going to try to put back the switch. Well, that is no problem. And here is my ground pin. So instead of going to the, I need to go to the other side. So if I bend this cap to this side, I have more space on the other side. Come. Okay. Yes, perfect. If this was it, then I really cut the corner just by not checking if that USB ground was a real ground. And it's okay. Yeah, that works. Okay. Now I just need to bend that pin a little bit. Okay. I need a little bit more light. Put the 50 ohms to the ground. Yeah. So instead of using the housing, I'm using now the first pin on this strip. And I put here the 50 ohms or 51 or 47, I don't know, I think I did 51. Yeah, so ground. So when I have this cable, instead of like this, I do like this. Same ground point. And yeah, I go over the resistor, ground there, and on the cap in the switch. Yes. Both stuck. Now I need to get the signal in the resistor in the cap. But my eyes really, let's see. Okay. Yeah, that's it. Good. Well, let's do a little test. internal power cord. Now, if it clicks when you clock, then it usually works. But I will show you frequency counter. You can see. Let's go to frequency on A. I need a BNC. Yeah, that is more or less 10 megahertz. That was the whole point. Okay, let's get my PLL ready. Okay, I started my PC. I have my PLL connected. Let's see, OpenCom and not connected. Why it says, oh, it's switch off. Switch it on. Close com, open com, read. Okay, my channel 4 is 50 megahertz. So I need channel 4. Now, okay. Check, double check. That should read 50 now. Yes, and this is external reference. As you can see, and this is the last significant one. So if you switch that off, it is spot on. Okay. Yeah, let's insert that. But I need another cable. SMA. Switch this off. You need to be so careful. Okay. Insert it in here. Switch it over. Power on. Okay. Channel 1. Clock. This could be good news. Or not. No, it still doesn't want to trigger. Okay, yeah, that makes sense. Maybe I need to remove the 50 ohms. Maybe on the input of the circuit there is also a resistor already, because I have here exactly 50 ohms, 50 megahertz, but I will make a screen print. Yeah, 50, but it is here 250 millivolt peak, so that is not enough. Yeah, I will remove the resistor. We need a lot more than 250 millivolts, so it's really. Well, now yeah, the connectors really, you need to do very, very well. So from the PLL apparently comes 1.4 peak instead of 4 or 5 volts. So I really hope that is enough. I will store that also. Yeah, let's see. I will just connect it. Okay. Power it back on. Well, it seems to be still be working. Clock. Oh wait, yes. Okay. But it is still off, so it's running on eternal or no? It is doing exactly what it should do because I programmed it to do this. I forgot it is not exactly 10. No, look, it does work. Okay, so let's put it to exactly 10 because that is what we want. Frequency, well, 10 megahertz. Okay, on. External ref, people, it works. Cool. So this is on its external clock on the PLL. And if I switch it off, I go back to the internal, switch it back on. Now it runs on its own clock. Well, it is not that far off, but it is just the idea, of course. So running on internal, as you can see, it is not that good, but also not really bad if I do faster. This is 10 megahertz. So you see, by default, it is not that bad at all. But of course, we want it precise. So if I switch it off, switch it over to external reference, switch it back on, you can see here it is not triggering. So yeah, now it's triggering. Puff. Okay, that's cool. That works. I put the time lapse. I will just put it back together. It's the same as the other video. And then I'm trying to show you another possibility to put this 50 megahertz as external reference if you only have 10, because this PLL is very nice, 6 channels, but it is above $100. I think it was €105, so maybe $125. And then you need to build it in a case and everything. So this is kind of, if you only use it for this, to have external reference, you pay 125 for this thing that costs 100. Doesn't make sense, but okay, that was a success. I will plug in the power. We put the external reference. Then we have the output right here, channel 1. And you have the frequency counter right there. Switch it on. And You can also have a look if I zoom out a bit here. You can see it's taking now 1 amp, and maybe it does more when I put the output on. Clock. Yes, it's now a little bit more. Yeah. Let's do, this could do 60 megahertz. Puff. Spot on. This is what you can do with external reference. So it can indeed do up to 60 megahertz and spot on. So as I mentioned before, this is a little bit of an expensive solution because the PLL is nice if you use it for multiple things, and I like it because I can program it with a computer and just say what frequency I want out of it. And it has 6 channels, so I can really do 6 different frequencies at the same time. That is very cool. But if you want to use it purely to run this one on the external reference, I have maybe a cheaper solution, and that is, I have here, no, this is the max. I have here the ADF 4351. I also changed it to external reference. This clock runs on 25 megahertz, but it has a possibility to change it to 10. So what I want to do is, and I will zoom in on the display, I will switch it over to external reference, set it in the menu to 10, and then I can maybe exit 50 megahertz, and then we can use this one as the 50 megahertz reference while connecting it to your lab 10 megahertz. So, okay, I switch off the PLL, so we don't use this right now. Then we're gonna play with this one. I need the USB for that. That is the round one. No, not this one. Yeah, this one. Okay, put that also on my desk now. That is really convenient. Okay, I will zoom in and I tell you what I mean with this. Okay, I have here this ADF 4351, 35 to 44 megahertz. So I could generate with this one the 50 megahertz. And this one I already modified that I can run this on external reference. And I made a video about that. And I also made it switchable so I can switch it over from internal to external ref. But this one runs on 25. Let me zoom in on the settings. This one runs on 25 megahertz. So if I switch it on, you can go to settings, and then you have here 25. And I tried this with my PLL running on 25 megahertz, and that worked fine. But the cool thing is I can set it also to 10. So I'm setting that to 10 megahertz. I switch it off. I will zoom out. I switch it to external reference, and then it should respond to external. So let me put my 10 megahertz. Don't get sick. Yeah. I will put here 10. I will put that on the external. External input. Come. Yeah. Then I need to check if it works. BNC SMA. So if I can output now a perfect 50 megahertz, then I can use that also, and that is a lot cheaper. So 50, it was already 50 megahertz point. It is exactly 50. So instead of using the expensive PLL, I can also use this. So now I will connect this to the UNI-T. Okay, the idea was nice. It all worked up to the fact that the output power is just too low. Um, I measure now on the oscilloscope and made the screen dump, and it's almost 500. It's 400, 440 millivolt peak. So that is just not enough. And out of my PLL came 1.5 volts. So that was cool. That is working. External reference on the UNI-T. Still, it's not that practical with the 50 megahertz because I'm really using now my 6-port PLL because it just outputs a higher voltage. This one outputs about 1.5, 1.6, if I remember correctly. While the test I did with the ADF, this one was like 440 millivolt. The max does a little bit more. The 550, I think. And but it is just not enough to make it sync on the reference. So you really need at least 1.5 volts, and then it works fine. So it does work. Thank you guys for your tips. And yeah, if you can somehow amplify this signal a little bit from 500 to 1.5 volts, then you have a cheap solution because the external ref works with 10 in. You can do 50 out. Could be something. So hope that helps. Thank you for watching, and hope to see you next time.